So as I mentioned in the other equilibria video, as far as the Year 12 equilibria topic is concerned, it's essentially two parts. The first part, which is what the other video covered, is essentially the qualitative side of equilibria. So if I make this change, if I increase this, this is what then happens. So it gives us a guide. It tells us that the position of equilibrium shifts to the left or the right, and we use the Le Chatelier's principle, but it doesn't really tell us any sort of detail. So it's a qualitative discussion of equilibria. What this video covers is the second part of the topic, which really looks at equilibria from a quantitative perspective. So essentially maths, or essentially a mathematical look at equilibria. Now, the first thing for us to start with is actually the last part of this title. So this is the topic. This is the title of this part of the topic. That's as given in the A-level spec, in the AQA spec. And so we just need to understand what is meant by homogeneous systems. Now, one of the things that we've already said in the previous video was the fact that equilibria, it needed to be a closed system. So the system is just essentially the reaction and its surroundings. We had a closed system, so essentially matter couldn't get in or out. So that's how the dynamic equilibria could be established, or that was necessary for the dynamic equilibria to be established. So now we're just looking at this idea of homogeneous. So here's a sort of description of what we mean by homogeneous system. So what we're talking about is when all of the reactants and products are in the same phase. Now, that perhaps only doesn't really help you, because you're now asking yourself, well, what do you mean by phase? So the second sentence here says, for example, they're all aqueous or gaseous with no boundary separating them. So you may ask the question, well, why have we used the word phase and why haven't we used the word state? The thing is that phase and state aren't exactly the same thing. So the key bit is this, with no boundary separating them. So the reason we don't use state and instead we use phase is if I basically draw something that you're quite familiar with. So we've got a container with oil and water, and they are immiscible liquids, so they do not mix, so the oil floats on top of the water. Now we could say that they're in the same state because they're both liquid, but they are not in the same phase because there is a boundary between them. So if there was a reaction that was going to take place between oil and water, and that's an if, it could only take place where the boundary is between them. So we do not have like a sort of we have essentially two systems, I guess, is one way of thinking about it, but with a point at which they meet. Now, it's not a big deal. I mean, this word phase is going to appear in a couple of other parts of the course. For example, when you look at catalysts in the transition metals part of the course, it's fine really for you to think about everything being in the same state, because really A-level, this idea of there being boundaries between two things of the same state, as far as I can remember, hasn't ever cropped up. But strictly speaking, we have to use the word phase. So here we're talking about everything's aqueous, or we're talking about everything's liquid, or we're talking about everything's gaseous. The other thing that was mentioned in the title of this sort of subtopic was the equilibrium constant. And that's denoted here with a capital K and a subscript C. Now the subscript C here basically refers to concentration. So you're going to actually come across a few different equilibria constants in the whole A-level course. We start with this one, the equilibrium constant Kc, and the C is just really referring to concentrations. Then I've just got a hypothetical reaction equation. So M is the number of moles, so M moles of A plus N moles of B, and then we've got the reversible reaction, the equilibria sign. Then on the reactants, we've got Y moles of C plus Z moles of D. So this is just a sort of a symbolic representation of a possible reaction. Now there is a particular method for giving the expression for the equilibrium constant. So Kc is our equilibrium constant, and the way it works is you look at the products, and I'll explain what these square brackets mean in a second, but it's square brackets whatever the substance is or species is, C, and then to the power of however many moles it is in the reaction equation, and then times, we don't put the times in just because it can get confusing if you do, or me trying to show it do, but if I need you to appreciate that if we say AB, then we mean A times B. So the other products, D, and to the power of however many moles that is, so Z, and then divided by, so basically the products go on the top, on the products of the numerator, or the numerator of the products, and then underneath are the reactants, so A, and then to the power of M, so however many moles, of course that could be 1, and then B to the power of N. Now square brackets, what that means is concentration, and then don't forget that that is measured in moles per decimeter cubed. So if we write A with the square brackets, then we're saying the concentration of A. And so what we've written here is essentially a general is essentially the general rule about how you write what we're going to call an equilibrium expression for this reaction. So it's going to be a fraction. On the numerator is going to be whatever products there are to the power of however moles, how many moles of each there are, and those products are going to be multiplied by each other. And then on the denominator is going to be the same, but with the reactants. So if we look at a concrete example, so we've got Kc equals, and we've only got one product, so it's ammonia. And the reaction equation has 2 moles being produced, so it's going to be squared. And then that is then divided by our reactants. So we've got nitrogen. There's only 1 mole of those, so to the power of 1, so we don't write that. We just leave it as N2, the concentration of N2, and then times the concentration of H2 to the power of 3, because that's the stoichiometry in this reaction. Now it's important that you understand this, that this whole thing here is the equilibrium expression. So sometimes in questions they ask you to give the equilibrium expression, and some people start putting numbers in and everything. The expression is before you put any numbers in. So you have your square brackets, you have the formula of your species, you have it to the power of whatever it's going to be, and so on. That whole thing there is the equilibrium expression. So you must also have the Kc equals as well. So let's have a look at an example question. So you will often, if not always actually, be given a temperature. So here it says at 827 degrees Celsius. Now, the reason they do that is because this is called an equilibrium constant, right? So therefore it's a constant. But temperature changes it. So what they're doing is they're saying at this temperature, what's the equilibrium constant? Because at another temperature, the equilibrium constant would be different. So it's constant at a particular temperature. So you're never going to have to use the actual temperature. They're just giving it out of point of accuracy. So the 827 degrees Celsius isn't actually important here. But just so you understand why they're giving you the temperature, it's because any equilibrium constant is constant at a particular temperature. So whatever we calculate here will be the equilibrium constant at 827 degrees Celsius. So they give us the reaction equation, they give us the concentrations for the reactants. This is a very sort of simple question, but it's really just to sort of help us get our heads around what's going on. So the first thing that we need to write is the equilibria expression. So we've got Kc equals, and then in our products we've got hydrogen. We're going to have the concentration of that times the concentration of iodine. Both of them, it's 1 mole, so to the power of 1, so we don't show that. Divided by hydrogen iodide. That's a 2 mole thing, so it's going to be squared. And you should always write the equilibrium expression like this, because that's typically 1 mark in a question. And if you just dive into the numbers and make a mistake somewhere, you don't even get this mark. So please make sure you always write the equilibrium expression. So now we insert the numbers. We know that hydrogen is 0.01, and we know iodine is 0.01, and we know that hydrogen iodide is 0.05 all squared, and so that equals 0.04. Now, what this does beg the question is, what about units? I haven't said anything about units yet. How could we know what units these are going to be? Now, typically, well, the units are derived from calculation. So if you think about density is, well, depending on whether it's chemistry or physics, but let's go with grams per centimetre cubed. Those are the units, because to work out density, you divided mass by volume. So often what you're looking at doing in the actual calculation tells you the units. So if we look here, we have got, basically we've got concentration squared. So the way we would work out the units is, in effect, to replace what we've written here with concentration, or with moles per decimeter cubed, and then we might find, or we will find, that some of these cancel out, and the units are going to depend on the original expression. So our final units are going to depend on the original expression, as we'll just look at an example now. So here we've got an esterification reaction. So we've got an alcohol and a carboxylic acid forming a ester and water. So if we were to write the Kc expression for that, so we've got our products. So that's our methyl methanoate and water. Both of those are 1 molar, so they're not to the power of anything. And then we've got our methanol and our methanoic acid. Now, let's just focus on the units. So each one of those square brackets is concentration, so each one is moles per decimeter cubed. So we can have moles per decimeter cubed times moles per decimeter cubed all over moles per decimeter cubed from the methanol, and moles per decimeter cubed from the methanoic acid. And if we look at that, we can simplify it. That's what we should always try and do. So those moles per decimeter cubed and those cancel out, and those cancel out. So what we would actually be left with in this particular example is that Kc would have no units. Now, quite often in exam questions, one of the marks will be to give the units or determine the units. And if you work it out to be no units, you absolutely must say that and write it. Please do not just leave it blank, because they will just assume that you haven't answered the question, as opposed to, you know, leaving it blank because you think there are no units. You must write no units. Here's another example. So we're just going to work out the units for this to see if there's any difference. So if we just write the moles per decimeter cubed, so that's the methanol at the top, and underneath we've got the carbon dioxide, and there's just one of those. And then we have got hydrogen, and that is squared. So now we try to simplify it, so we can cancel out those two. So we're left with 1 over moles dm minus 3 all squared. I think the thing to do now is to expand those brackets. So we've got 1 over, and so we've got moles squared, and then dm to the minus 6. And then when you've got 1 over and you want to get to everything so that it's not 1 over, you reverse the sign. So we're going to have moles to the minus 2, dm to the 6. I am sort of rather assuming a little bit of maths knowledge there. So I want to show you the approach, but I'm not really explaining how you do it from a mathematical point of view, just how you do it, assuming you know the maths. Now, what does Kc tell us? Well, remember, Kc is an outcome of a mathematical expression which has a numerator and a denominator. So if Kc was approximately 1, what that would tell us is that the numerator and the denominator were the same size. And if we're thinking that the numerator is essentially the products and the denominator is the reactants, then roughly speaking, because there could be to different powers, but roughly speaking, a Kc of 1 means that the position of equilibrium is approximately in the middle, because the numerator and the denominator are essentially the same sides. If we think that Kc is greater than 1, then what that's telling us is that the numerator is greater than the denominator, and the numerator is the products, the denominator is the reactants. So the position of equilibrium lies somewhere along the right, or to the right. And if Kc is an incredibly large number, so e.g. 1 times 10 to the 10, so it's a very large number, that's telling us that the numerator is significantly larger than the denominator, so the concentration of products is significantly larger than the concentration of reactants, and so in effect we could say that the reaction has essentially gone to completion. Similarly, if Kc is less than 1, then that's telling us that the denominator is larger than the numerator, so that means there is more reactant than product, or reactants than product. So in effect, the position of equilibrium lies to the left. And then if Kc is very, very small, so something like 1 times 10 to the minus 10, that's telling us that the denominator is significantly larger than the numerator. That means there are significantly more reactants than products, and we could effectively say that the reaction hasn't taken place. So Kc is giving us a much clearer idea of where our position of equilibrium lies than anything Le Chatelier could do. In fact, Le Chatelier only told us that it got shifted in one direction or another, but it never told us never gave us any sense of where the position actually lay. Now, it's possible to determine the equilibrium constant for a reaction from experimental data, from actually doing a practical and then doing some analysis of that practical. It's possible to determine the concentration of things at equilibria. And quite often questions are structured that way, so they will provide you with information, so the number of moles or whatever at the start of the reaction, and then they will give you the number of moles of one of the substances at equilibrium. And it's then possible actually to determine all of the information you need to work out Kc. But one thing to help you do that is this mnemonic here, ICE. That will make a bit more sense when we see an example, but essentially the I stands for initial, and it'll be initial moles. Change, C, the C is change, so change in moles, and then E is equilibrium moles, or moles at equilibrium. So it allows us to perform calculations that are based on experimental data. So here's an example here. So they're telling us that 5 moles of A are mixed with 5 moles of B. So those 5 moles of A and 5 moles of B are how much we're adding together. So they are the initial moles of A and B. And if they haven't yet been added together, then when we look at our reaction, we see it's making C. We know that until they're added together, there is no C. So the initial moles of C is going to be 0. We're told the volume of the container, which is important because remember, concentration is moles divided by volume. And then we're told an equilibrium is established and that this contains 3 moles of C. So we're only told the number of moles of C at equilibria. And then we're asked to find Kc at this temperature. So they presumably did give us a temperature as well, but I seem to have missed that off. So the way to approach this question is to write out the reaction equation and to give yourself a little bit of space, because essentially you're going to be writing a grid underneath. Now, I'm in the habit of writing the molar ratios above. You'll understand why these are necessary, but I just think it makes things a little bit clearer, which is why I actually write them. You may think that they're just implicit anyway, so you don't need to do it, but it's up to you. So we're just going to use our ICE mnemonic to sort of help us lay out the grid. So it's going to be initial moles then it's going to be the change in moles, and then it's going to be equilibrium moles. So it's important to lay things out nice and clearly. We were told that A at the beginning was 5.0. We were told that B was 5.0. And this is something that you have to think or understand must have been the case. But if they haven't yet been mixed, we must have 0 moles of C. And then the only other value that we were given was the number of moles of C at equilibrium, which is 3.0. So other than just realizing that there is no C at the start of the reaction, there isn't really any thinking. We just that's happened so far. We've just basically laid things out, got things ready for what we now need to do. So the next bit then is to fill in the gaps. So if we look at C, we've gone from 0 to 3.0. So that means we have had an increase, and I'm going to put a plus sign because it's important to remember when it's an increasing, when it's decreasing, of 3.0. Now, to make C, A and B have to react, and we look at our molar ratios then to think about how much A and B must have reacted. And if we look at the molar ratios of B and C, we can see it's 2 to 2, or in other words, 1 to 1. So that means to make 3 moles of C, I must have used 3 moles of B. That means, though, that we used it, so that's why we're using a negative value, so it's decreased. The change in moles is a decrease of 3 moles. And that now gives us the equilibrium moles of B, so 2.0, so 5 minus 3 is 2. And then if we consider A and we consider the molar ratios of B to A, it's a 2 to 1 ratio. So for every 2 moles of B, we need 1 mole of A. So we've got 3 moles of B being reacting, so we need 1.5 moles of A. So that means the equilibrium moles of A is 5 minus 1.5, which is 3.5. And so now we have our equilibrium moles. Now, even before we get to our equilibrium expression, we know that that what we're actually needing is concentration. Now they've given us the volume of the container as 12 decimeters cubed, and that will be the volume for all of the for A, B and C, because they're all in a closed system, they're all in the same container. So what that means is that the concentration of A equals the number of moles, which is 3.5, divided by the volume, which is 12, which gives us a value of 0.292 moles per decimeter cubed. The concentration of B is the number of moles at equilibrium, which is 2, divided by the volume, which is 12, equals 0.167 moles per decimeter cubed. And then finally, we've got the concentration of C, which equals the number of moles at equilibrium, which is 3, divided by 12, equals, and then 0.25 moles per decimeter cubed. So now we have the concentrations that we need to use in our equilibrium expression. So our equilibrium expression for this question is C, the concentration of C to the power of 2, all squared, and then the concentration of A times the concentration of B squared. And we knew that A was 0.292, this is from the previous slide. B concentration equals 0.167, and then C is 0.25. So now we put those numbers in. So we get 0.25 squared over 0.292 times 0.167 squared, and that equals 7.7. Now we don't know what the units are, so we'll just put right units for the moment. So we need to put our units into the equilibrium expression. So we've got moles per decimeter cubed, and then this is C, so squared, over moles per decimeter cubed times moles per decimeter cubed squared. So we can cancel out the 2 moles per decimeter cubed squared. So that equals 1 over moles per decimeter cubed. Then we reverse the signs, so moles to the -1 decimeters cubed. So our final answer is 7.7 moles to the -1 decimeters cubed. Now, often in questions like that, you're not always given the volume, which means you can't work out the equilibrium concentrations. And so what happens is most students think, oh my God, there's a mistake in the question. And almost certainly there isn't a mistake in the question. So when that happens, when you're not given a volume and you suspect, and your initial reaction is, well, I should have been given a volume, how else can I work out the concentrations? Then what you need to do is check the total number of moles on each side of the balanced equation. A bit like when you did pressure and you were looking at how many moles on the left, how many moles on the right. If they haven't given you the volume, you should find then that the total moles on both sides is the same. And if you think about it, that will mean Kc has no units. Now, why does that mean that we don't need volume? Well, let's just have a look at that. Okay, so we have our Kc expression, or equilibrium constant expression, for this reaction. Now, let's change those concentrations to moles over volume. So all I've done is I've just made it clearer what the square brackets are. They are the concentration, which means the moles of, for example, methyl methanoate over the volume. Now, all of these substances are in the same container, which means the volume that these substances are in are all the same, which means that we can cancel out the volumes. So what we are actually left with is the moles of HCOOCH3 times the moles of H2O, all divided by the moles of methanol, moles of CH3OH, times the moles of the methanoic acid. And now you can begin to see, or now you can see, why the volume wasn't necessary. So what you'll find is if you have the total number of moles on each side of the balanced equation, if they are the same, then volume isn't needed, because in effect volume will have cancelled out. So if you find that you don't get volume in a question, please double check that first. Okay, so this is how a question could actually be presented. So they're telling us the number of moles of ethanol and the number of moles of ethanoic acid that were mixed together. So that's the number of moles. They must be the initial moles. So when they say were mixed together, the values before that are initial moles. It's in a sealed container, so we know it's a closed system, and placed in a water bath at 25 degrees Celsius. Now that isn't really that important, but that would be what you would actually do, which is why they state that. So they only ever really state accurate things. The mixture was left for a week, during which time the following equilibrium was established, and then they've got an ester reaction. The equilibrium mixture was titrated with sodium hydroxide of 0.5 moles per decimeter cubed concentration, and 30 centimeters cubed of that alkali were required for neutralization to occur. So remember, this is neutralization at equilibrium. Use this information to calculate a value of Kc for the equilibrium reaction at 25 degrees Celsius. So first thing to sort of say is that they've not given us a volume. Now, so this is where you double check and you look, what's the total number of moles on the left? Well, it's 2. What's the total number of moles on the right of the reaction equation? It's 2. So there is the same number of moles on both sides. So that is why we don't need volume, right? So we're just going to need the moles of each. Now they've given us the initial moles of ethanol and the initial moles of ethanoic acid. But then those are the only molar quantities that they've given. The thing that's a little bit different here, but this shows how you could determine it in a practical sense or an experimental sense, is they've told us about an alkali, they've given us a concentration, and they've told us how much was needed for neutralization to occur. So if we look at the reaction mixture, or we look at the equilibrium, reaction, only one of these 4 substances is an acid. So that's ethanoic acid. So what that's saying is this amount of alkali, so the 0.5 moles per decimeter cubed concentration with 30 centimeters cubed of alkali was required to neutralize, and it must be to neutralize the ethanoic acid. So essentially they're giving us the information to know how much ethanoic acid there was at equilibrium. All right, so that's like another piece of information. So that's actually the first thing that we've got to do. So moles of NaOH in titration, or added, NaOH added, that's how we'll do it, it doesn't really matter, equals, and it's, remember, moles is volume times concentration, but it's volume in decimeters cubed times the concentration, so that equals 0.015 moles, and the ratio of NaOH to ethanoic acid is 1 to 1. So therefore, the moles of ethanoic acid at equilibrium equals 0.015 moles. So now we've got moles of ethanol at initial, or initial moles of ethanol, we've got initial moles of ethanoic acid, and we've got equilibrium moles of ethanoic acid. So from that we should be able to construct our ICE table, which is what we're going to do now. Okay, so we have 0.049 moles of ethanol, and to start initial also we have 0.047 of ethanoic acid, and before they're mixed we cannot have any product. So we have 0 of the ethyl ethanoate and of water, and then we used the titration to determine the number of moles of ethanoic acid, which was 0.015, sorry, at equilibrium. So from that we can now determine the change. So we have a change of 0.032. All right, so if we have got, if our ethanoic acid has decreased from 0.047 moles to 0.015, then that is a decrease of 0.032. And the rest now is it's quite generous to us in that the ratio, the molar ratio for everything now is 1 to 1 to 1 to 1. So if we know the change is minus 0.032 for the ethanoic acid, it must also be that for the ethanol. So that gives us an equilibrium moles of ethanol, and then if those are both decreased, sorry, if the reactants are both decreased by 0.032, then the products must have increased by that amount. And we can say it's the same amount because it's a 1-to-1 ratio across the whole reaction. So that now leaves us with, or gives us, the final equilibrium moles for all of the substances in this reaction equation. So now we're ready to do the next bit, which is to take these numbers and use them with the equilibrium expression for this reaction. So let's write our equilibrium expression. So we have our products, ethyl ethanoate, and we have water as the other product. Both of those are the power of 1. And then ethanoic acid is one of our reactants. So I'm writing the expression, sorry, should still be concentration, because that's what they would expect, and that's what the mark scheme would say. However, when we come to do the calculation, we can simply put the moles in. So we know that the volumes cancel out, so we can simply put the moles from the previous slide. So that is going to equal 0.032, because that was the equilibrium moles of the ethyl ethanoate, times 0.032, which was the equilibrium moles of water, divided by 0.015, which was the moles of ethanoic acid, times 0.017, which was the moles of ethanol. So we put that into our calculator and we get 4.02, but of course when we look at the data we're given, actually in the case of the concentration of the sodium hydroxide, that's actually only to one significant figure, which is not normal and wouldn't usually be the case in a real exam question. But if we're to be strict as far as what we were given here, we've been given the least precise information is one significant figure, so our final answer will be to one significant figure. Although, let me just say that in a real exam, never ever ever give an answer to one significant figure. It will never be appropriate. Regarding the units, because we were able to cancel the volumes out, that was because there were an equal number of moles on both sides of the reaction equation. That also means that there will be no units. So whenever you get a reaction in which you're not given the volume, and you're not given the volume because there's an equal number of moles in total on both sides of the reaction equation, that also means that there'll be no units. So if we even just look at what we've got here, moles per decimeter cubed times moles per decimeter cubed divided by moles per decimeter cubed times moles per decimeter cubed. So there will be no units, they would all cancel out. Now, there is another type of question that they can ask, and it's one that involves our introducing an algebraic term, and it often throws students. It doesn't come up very often, but it comes up often enough for you to need to worry about it. So in these questions, you're typically given Kc, and what you're having to work out is a concentration. So let's have a look at this reaction. So again, they're giving us a temperature, but that temperature is just there to say, that the Kc that we're given would be true for that temperature. Then it says, suppose 1 mole of hydrogen and 1 mole of iodine are mixed together in a 1 decimeter cubed vessel. It's actually they're keeping the volume very nice sort of sums here. What are the concentrations of the hydrogen iodide, the hydrogen and iodine at equilibrium? So we're actually having to work out the concentrations for all of the substances in this reaction. Now, the way we go about this is no different to what we've done up to this point. So we're going to construct an ice table. Okay, so here's our table. Now, we're told that we are mixing 1 mole of hydrogen, and we are mixing 1 mole of iodine. And if they are being mixed, then an equilibrium is being formed. We don't yet have any hydrogen iodide. And that's it for the moment, right? Now, what we do is, the reason that this is now introducing an algebraic term is we are going to let the change in one of the products in this equation, we're going to let the change be y. So I is going to decrease by y, and so the equilibrium will be 1 minus y. And if we think about our molar ratios, iodine to hydrogen in this is 1 to 1. So if iodine decreased, or the change was minus y, then it's going to be minus y for hydrogen too. So again, 1 minus y. And then if we look at the change in hydrogen iodide, we must have an increase in 2y. Apologies. The reason it is 2y is because of the molar ratio. So the molar ratio of hydrogen to hydrogen iodide is 1 to 2. So change in y of hydrogen would mean a change of 2y in hydrogen iodide. So our equilibrium moles is 2y. So we've now got our ice table. Now, they've been very kind in that they've given us a volume of 1 decimeter cubed. So actually our moles in this instance will be our concentration, because moles divided by volume is concentration. So moles divided by 1 will be the same value. But actually we didn't need the volume. If you look at the original reaction equation, it's the same total number of moles on both sides of the balanced equation, so the volume would have cancelled out. But anyway, that's by the by. So let's now look at our equilibrium expression for this equation. So now we can introduce our values. So it's going to be 1 minus y times 1 minus y over 2y squared. And we know that Kc is 0.02. Now, we can rewrite the right-hand side of this equation, or we can write it differently, I should say. And actually, this other way of writing it is going to make things a little bit clearer. So all I've done is instead of writing 1 minus y times 1 minus y, I've just done 1 minus y squared. Now, the reason that makes the next step easier is because what we can hopefully see more clearly is that we could square root everything. So the square root of 0.02 is 0.14, and then the square root of 1 minus y all squared is 1 minus y, and the square root of 2y squared is 2y. And now we just need to resolve what's there, so we're going to multiply both sides by 2y, so we get 0.28y equals 1 minus y. So that means that 1.28y equals 1, which means that y equals 0.78. Now remember, y here is the change in moles, so we're saying that the change in moles is 0.78. So now we have to return back to the ice table that we did on a previous slide, and now insert what we know y to be, because that will now give us the number of moles of each substance at equilibrium, and from that we can work out the concentrations of each substance at equilibrium, which is what the question was actually asking us to do. It was asking us to work out the concentrations at equilibrium of hydrogen iodide, hydrogen and iodine. So here's part of our ice table. So we now know that the hydrogen is decreasing by 0.78, as is the iodine. So that now gives us an equilibrium moles for both of those substances of 0.22. And then we have to sort of just, when we're working out the change in the hydrogen iodide, obviously if the hydrogen and iodine are being used up, that means hydrogen iodide is being formed, so it's going to be a positive change. But the other thing we have to consider is the molar ratio, and for every 1 mole of hydrogen we would form 2 moles of hydrogen iodide. So if our change, if we're using up 0.78 moles of hydrogen, then that means we are going to form 1.56 moles of hydrogen iodide, and that means our equilibrium moles is 1.56. Now, this question was extremely kind, and in that when it gave us the original information, the volume that they gave us was 1 decimeter cubed. So to work out the concentration, it would be the number of moles divided by the volume, and the volume is 1. So actually it's very straightforward now to give the final concentrations, or the equilibrium concentrations, for each of these substances, because it's going to be the value that we've got in terms of moles at equilibrium. So our concentration of hydrogen iodide at equilibrium is going to equal 1.56 moles per decimeter cubed. For hydrogen, it's going to be 0.22 moles per decimeter cubed. And then finally, for the iodine, it's going to be 0.22 moles per decimeter cubed. So that's basically the end of this video. This algebraic stuff that we've just done, what I'd say about it is that it's a question, or a type of question, that doesn't come up very often, but it does come up. And so what tends to happen is you do it with students, they get it, and then they forget about it, and then it appears in a question maybe months later, and they struggle and they're not sure what to do. So it's very important whenever you're doing any exam or exam style questions, that when something perhaps unusual comes up, something that isn't the norm, is to sort of almost is to make a note of that, make a special note of that. Maybe have, I don't know, a document or a file or something where you're making a record of interesting or unusual questions, so that when it comes to revision you can make sure that you pay careful attention to those, because they're probably the ones that are more likely to catch you out. But otherwise, I hope that was helpful, and if you've got any queries, just let me know.